We are ready to begin our study on matter and the phases of matter. 2A and 2B talk about what matter is and how to classify matter according to certain characteristics. 2C and 2D, those sections will discuss the phases of matter and how matter changes from one phase to another. We are ready to begin. Notes 2A and 2B, understanding matter and classifying matter. Ready. What is matter? Matter is anything that occupies space and has mass. When we talk about occupying space, we're talking about the volume of a piece of matter, whether liquid, solid, or gas. All matter has volume. Mass is stuff that makes up the piece of matter, the atoms and the molecules, what all things are made of. The more mass an object has, the more the object will weigh, as we'll talk about in another lesson. Light, sound, heat, those are not kinds of matter, those are energy. Light has no mass, takes up no space. The same for sound and heat. Those two things do not take up space, they have no volume, they have no matter, so they are different forms of energy. And there are also other forms of energy as well, such as magnetism and electricity, among others. But matter is anything that occupies space, which means has volume, and anything that has mass, which means is made up of atoms and molecules. Ready? Modeling matter. Here you see representations, models of two very common substances. The one on the top right, that's a water molecule. The one on the bottom right, that's a representation or a model of a sugar molecule. You probably already know the chemical formula for water is H2O. But you look here and you will see, I'll write it over here in case that's hard to tell, C6H12O6. 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Now I want you to notice, because water and sugar are each going to have the exact same makeup every single time. The law of definite proportions says just that. A substance is something that's always made up of the exact same ratio of atoms in a molecule, or in other words, made up of the exact same stuff every single time. Top picture, water molecule. Bottom picture, sugar molecule. Water is always 2 hydrogen atoms and 1 oxygen atom. You will never see water anything else. If we were to put a 2 here after the oxygen, it'd have to be inside parentheses, I just needed room. That would no longer be water. That would be something called hydrogen peroxide. Water is going to be H2O every single time, no exceptions. Now there are different kinds of sugars. This kind is called glucose. And once again, you're going to have the exact same ratio every single time. 6 carbons, 12 hydrogens, and 6 oxygens. No other way to put together a glucose molecule, and nothing else will ever have C6H12O6 either. And that goes exactly the same for every substance, whether an element or a compound. Ready? Brownian motion. Matter's particles are always in constant motion. Tongue stumble once in a while, but just shows them human. This is also part of the particle model of matter, which we can talk about another time. Matter's particles are always in constant motion. Think of the air. The molecules that make up the air that we breathe, they're always moving. There's never a time where the particles are not moving. Now look at your tabletop. The table appears to be stationary, not moving at all. But if we were able to get an extremely powerful electron microscope and we looked at the atoms and the molecules, we would be able to see that those atoms and molecules, the particles, are moving, and depending on how closely packed together those molecules are, the speed of the motion will vary. In fact, it's the speed of the motion of those molecules and the distance between each one that will determine if we have a solid, a liquid, or a gas. The next set of notes will talk about that in more detail. But Brownian motion says particles are always moving. Diffusion. Particles mix without being forced to. Because of this Brownian motion, these atoms and molecules are constantly moving, allowing, sometimes quickly, sometimes slowly, mixing of different ingredients. For example, we put our sugar into our tea. Stir one of those glasses and the sugar is going to mix very well with the tea. Take a second one and just put the sugar in, but don't stir. Now, most of the sugar is going to end up sinking to the bottom, but some of that's going to continue to move throughout the liquid. It'll taste a little funny to you. However, you're going to get some Brownian motion and some diffusion. Try this experiment. This is very easy to do. Just get a food coloring. Get that off there. Take food coloring. Take the same two identical glasses. Take two identical glasses, fill them up with the same amount of water. Put 1 drop of food coloring into one glass and the same size drop into another glass. Stir just one of those glasses and you'll see the color mix with the water very, very quickly. Let the other one just sit, and it'll take a while, but eventually, because of diffusion and Brownian motion, eventually the one you did not stir will start to look very, very similar, if not almost exactly like the one that you did stir. Something I can show you during class, or something very easy that you can do on your own. You ever been in a room and somebody, even across a large room, sprays some perfume? You're kind of far away from it, but eventually you're going to start smelling that perfume. That's because the molecules in that perfume get forced into the air with a pretty good amount of force and speed, and those molecules will eventually make their way throughout much of the room. So people, even on the other side of the room, may be able to smell that perfume. I don't do that in class because many people don't like that scent, or I know someone who, her being around perfume is just not a good thing because of her health conditions. So I can't do that one in class. But Brownian motion and diffusion are going to allow particles of different substances to be mixed together without being forced. Ready? Measuring matter. How do we measure matter? Well, it depends on what phase the matter's in, solid, liquid, or gas. Mass is the amount of matter in an object. That's your definition. In fact, this page is mostly definition right here. When we take an object's mass, we're trying to figure out how much stuff is in that object. When we measure the volume, we're measuring how much space an object occupies. Two different pieces of matter can have very, very, very different masses, even the same size. Let me try that again. Different amounts of masses, but still have the same size and shape. Think of a bowling ball and a basketball. They're very close to about the same size. Basketball may be a little bigger in size, but the heaviest bowling ball, 16 pounds, is going to weigh a whole lot more. So these are two completely unrelated objects. There can be very large volumes that have very little mass, and there can be very small volumes that have a lot of mass. Think of something like a shot put, a small volume, but a lot of mass and weight. Both of these, however, when calculated and put together in the correct way, give us something called density. So if we can measure or know the amount of mass in an object and either measure or know the volume of the object, we can find the object's density. The good thing about that is no two substances have the same density. Some are close to each other, but no two substances will have the same density. Scientists can calculate the density of an unknown substance and compare their calculations to charts that many, many, many scientists over many, many, many years have already calculated to help determine what a substance might be. If we measure a small amount of solid and calculate the density, we're going to use the unit gram per cubic centimeter. If we take a small liquid and measure the density, then we're going to use gram per milliliter. Now, one thing about this is that the cubic centimeter of a solid is exactly the same volume of a milliliter of liquid. In fact, the definition of a milliliter is how much space a cubic centimeter of a solid takes up. That is called a milliliter. So in a couple of our assignments, we might want to remember this. Of course, I'll remind you at the correct times that a cubic centimeter is exactly the same size as a milliliter. We use cubic centimeters for solids. We use milliliters rather, for liquids. Example, take the density of a 500 gram object, solid, that has a volume of 150 cubic centimeters. You will get approximately 33 1/3 grams per cubic centimeter. For a liquid, 125 grams of a particular liquid, and you have 25 milliliters of that liquid, you would then divide and get 5 grams per milliliter. The calculation is quite simple. It's just knowing which way to go. And it's easy to understand. It's also easy to mix up. But density is an equation simply dividing mass divided by volume. Ready? Measuring instruments. What do we use to measure certain objects, and what quantities do we want to measure? We step on a scale in the bathroom to weigh ourselves. That's called a scale. You might do that at football practice. You might do that at a doctor's office. But if you want to measure how much matter makes up your body or another object, you're going to use an object called a balance. When the time comes, I'll take out some of the measuring equipment, show you how to use that, and give you a chance to do so. Something small we're going to measure in grams, such as a paper clip. Something large like you or your table, we're going to measure in kilograms, because kilogram is 1,000 grams. In the metric system, we will use a unit called a newton instead of a pound. I mentioned this before. I weigh approximately 220 pounds. However, knowing that 1 pound is approximately 4.44 newtons, if I do 220 times 4.44, I'm going to be over 900, greater than 900 newtons. I'm not going to go around and tell people I weigh 900. So they are very, very different units. We use a scale to measure an object's weight, and I'll show you different kinds of scales when the time comes. To measure distances and lengths, we use something called a ruler. You're used to a 12-inch ruler or a 6-inch ruler. A yardstick is a ruler. A meter stick is a ruler. Then 1,000 millimeters make up a meter. So a millimeter is 1,000th of a meter. A centimeter is 100th of a meter. And a kilometer is kind of the metric equivalent to a mile. 1,000 meters. Think of a meter stick. Think of 1,000 of those end to end. That's a kilometer. A kilometer is approximately 6/10 of a mile. And a mile is a tiny bit more than 1.5 kilometers. For liquid volume, for small objects, we're going to use a beaker or a graduated cylinder for smaller amounts of liquid. We might measure milliliters or liters. Of course, more liquid is going to require a larger beaker or a larger graduated cylinder. And a liter. For larger ones, you go to the store, you might buy a 2 or even a 3-liter bottle of soda. Most of the water bottles you will drink are half a liter. Some are larger, of course. Solid volumes. There are formulas for nice, neat shapes, such as a rectangular solid, a box, or a sphere, like a basketball. There are mathematical formulas for nice, regularly shaped objects. But there are also different kinds of methods to use for things that are not regularly shaped. In fact, much of the matter we deal with every day does not come in a nice uniform shape. We might have to do other ways of finding that, things that I will show you during class. For things that are smaller, we'll measure the volume in cubic centimeters. For much larger volumes, such as this classroom, I might measure in cubic meters. And in fact, I might even do something more like decimeters for something as big as this classroom. Deci means 10, so a decimeter is 10 meters. The unit cubic centimeter is for small solids, and the unit milliliter is for small amounts of liquids, as I showed you before. Ready? For the classification of matter, what does classify mean? Well, that means to put into particular groups. When we classify we're making a scientific model. Okay? We classify matter into, well, the three we're going to talk about the most: solids, liquids, and gases. Some matter is in the plasma phase as well. But when we put a piece of matter into solid, liquid, or gas category, we're classifying. We're making up a scientific model. We classify matter to distinguish among the different kinds. Solids have particular properties that liquids do not have. Liquids have particular properties that solids do not have. And the same can be said with gases. Now, liquids and gases are both fluids because they both flow, allow an easy change of shape. We'll talk more about the characteristics and the details of the three phases of matter in the next set of notes. We classify matter according to its properties, and that's basically how close together the atoms and the molecules or the particles are. In solids, those particles are much, much closer together. In liquids, particles are still pretty close together, but not quite up against each other. And in gases, the particles are very far apart and move a whole lot faster. And again, more about that in our next set of notes. Ready? Here's some physical properties. First of all, let's distinguish between physical and chemical properties. In a physical property, you're going to see this in print in just a little bit. We are talking about only things that make up the appearance of that piece of matter. And you'll see some very common examples in just a moment. We don't change the matter into something else. That would be called a chemical property or a chemical change. For a physical property, we can observe and measure, and here's the key word once again, without changing the matter into something else. We're talking about only the appearance when we're dealing with a physical property. What does the substance look like? Now remember, appearances can relate to all five senses. So when I say appearance, I may be talking about a sound. That's an appearance to the ear. Or texture, that's an appearance to the sense of touch. Here are a few very common physical properties. There are others. Color, hardness, density, shape, texture, again, that's how something feels. Conductivity means how well does electricity flow through the object. These are all physical properties, and you may be able to come up with some more. But physical properties allow us to observe and measure without changing the matter. We're talking about only the appearance. For example, maybe I can do it with the color here. I have sort of a purplish color, and I paint instead. And when I do that, you can see I have the same word, of course my handwriting, but a different color. Okay, so if I just paint over something, paint the house from white to brown, all I did was change the color of the house. I did a physical change dealing with a physical property. Ready? In a chemical property, here's the key term about getting a chemical property or change. We get a brand new substance. Again, my handwriting's not the best. Let me try that again. New substance, something that wasn't there before. Hydrogen gas and oxygen gas, and I'll explain about the twos another time, they come together and they make a liquid called dihydrogen monoxide, which we know as water. Again, I'll explain about the little bitty numbers at other times. In fact, when we do the periodic table in chapter 3. Chemical properties talk about how matter reacts with other matter. What kind of changes happen? And we're talking changes into something new, not just the appearance this time. Iron rusting, that's a chemical change. See, iron is actually a combination, or rust I should say, is actually a combination of iron and oxygen that come together to make a compound called rust. And there will be other numbers up here that we'll talk about when we balance equations later on. But this is your chemical formula for rust. And no other substance will rust because rust is made up of iron. That's why chrome will not rust. And that's the reason many faucets have chrome coatings over them, because the chrome is not going to rust and ruin the pipes. Chemical changes cause a new substance. They take whatever we have and turn those substances into something new. And we'll talk about the 4 different kinds of reactions in a couple chapters from now. Hydrogen and oxygen, I showed you a little while ago, that gives us water. H2 plus O2 gives us H2O. Of course, then we have to do other things to make that equation written correctly. Sodium, here's something else you're very familiar with. And here, this doesn't require any numbers because 1 atom of sodium will easily combine with 1 atom of chlorine. There is something else involved to give us 1 molecule of sodium chloride. In fact, if I put a 2 here and a 2 here, then it's correct. So I should say it this way then. 2 atoms of sodium combine with 2 atoms of chlorine to give us 2 molecules of sodium chloride. And again, I'll tell you about that 2 and that 2 and why they're written exactly that way a couple chapters from now. But this is a very common substance called sodium chloride, which we know as table salt. Thing is, sodium is a very deadly solid. Drop sodium in water, we get an explosion, and possibly even fire. Chlorine is a very deadly gas. Take 1 sniff of chlorine directly from a container, that's deadly. Have about a 95% chance of death by doing that. Chlorine bleach or chlorine in the swimming pool, there are reasons why it's not quite as dangerous, but can be. But table salt, this is a solid that we eat. So we take 2 very deadly poisons and they come together and they make something that we eat. And if we eat in the correct amounts, very healthy for our bodies. And more details about that during our periodic table chapters. Ready? Hydrogen and oxygen and carbon I showed you a little while ago. Those give us different kinds of sugars. I showed you glucose, C6H12O6. There are a few other kinds as well. Now ready. A pure substance is a piece of material that's made up of only 1 kind of element or compound. Well, we mentioned water. Try again. Forgot to hit that. Water is a compound because water is made up of at least 2 different elements put together exactly the same way. But water is going to be exactly the same every single time. So will salt. And so will glucose, that sugar I mentioned a moment ago. Other pure substances are just a single element. Gold, chemical symbol is Au. We have to breathe oxygen, but most of the air that we breathe is not oxygen, it's nitrogen. Okay. These are elements, these are compounds. When there are 2 or more different elements combined, we call that a compound. Take that off and continue. Ready? All right. Oh, not a mixture. I forgot about that line. Mixture, we're about to see what it is. There are different kinds of mixtures as well. Now we are ready. An element is made up of all the same kind of atom. Okay? So I put the symbol for gold up there just a moment ago. The chemical symbol for gold, element 79, is Au, and that comes from the Latin word aurum, which means gold. So if I have a chunk of gold, I have something that is nothing but gold atoms. So if I have a substance that's made up of exactly 1 kind of atom, there may be millions and millions and millions and billions of them. I have an element. Okay, something else that we use quite often is copper in our pipes and in our wiring. Copper is an element because no matter how big of a chunk of copper we have exactly the same element, the same kind of atom. In a compound, as I showed you a moment ago, 2 or more different elements that are chemically combined. And I gave you a few examples of those as well. These are pure substances because they're the same way every single time. Ready? Oh, one more example, salt, sodium chloride, NaCl every single time. Ready? In a mixture, think of this. We mentioned the sugar in the tea a little while ago. That's a mixture because we can put any amount of sugar we want in any amount of tea. The taste will be different, the concentration will be different, but we're still going to have sugar in tea. The sugar may be dissolved, but it's still going to be in that tea, and we'll talk about how we know that. In fact, I'll go ahead and give it away a little bit now. Definitely by taste. Let that tea sit long enough to evaporate. You'll see the sugar settle to the bottom of the glass. There's no different formula. Think of throwing a bunch of pens and pencils together in a great big pile. Doesn't really matter how many pens we have or what kind even. Doesn't matter how many pencils we have or what kind even. We got a mixture of pens and pencils. There's no chemical combining. I can reach in there and pull out a pen the same as if that same pen was in a different mixture of pens and pencils or even some other writing utensils like a magic marker. Each substance will maintain its own properties. Even if the sugar dissolves in that tea, the sugar is still going to be C6H12O6, just smaller amounts spread throughout the glass. All we're doing is separating those molecules of sugar and causing them to diffuse and dissolve in the tea. Now, diffusion and dissolving and different kinds of mixtures, that's more detail in a later chapter. But in a mixture, every substance maintains its own properties. There's no change into what kinds of substances we have. Pretty much just how many and how much of each ingredient. Ready? Two main categories of mixtures: solutions and heterogeneous mixtures. And again, a later chapter is going to give us much more detail about these. But look on the top right, you see the salt is being dissolved in the water, and if we taste that, we're going to taste the salty water. Saline water. Saline is a more scientific word for salt. Now, you see in the small print up there the word homogeneous. Right here, homogeneous mixture. That word means same. H-O-M-O means same, and geneous refers to the appearance. If I pick up that glass of salt water, no matter how I look, what angle I look at the water itself with the salt dissolved, I'm going to see the same thing. But if I look at something like a taco, and I picked up that taco and I turn to view from different angles, I'm going to see different things. A tomato in one place, I hate tomatoes though, so I don't put those on my taco. Cheese in another place, lettuce. Same with the pizza and the mixed vegetables. I can move that eggplant over to this side maybe. It's the same salad, now the ingredients are just mixed around. Hetero means different. And geneous means appearance. So heterogeneous mixtures have different appearances as I view them from different vantage points. Here's your definition again. Homogeneous has the same appearance all throughout the mixture. No matter how we look at that mixture from whatever angle, we're going to see exactly the same thing. Air. Well, air hopefully is invisible. If it's not, then we got some pollution going on. But air is invisible, so air will have the same appearance no matter how we look at that. A nice, clean piece of stainless steel. Now, there may be dirt and other things on there making it look dirty, but the stainless steel itself, polish that off, perfectly clean. See the spoon in the cup over there? Not the shape, but the actual stainless steel that makes up that spoon has the same appearance from all vantage points. Alloys, we'll talk more about alloys another time, but these are different kinds of metals that are melted down and mixed together and then frozen back into a solid. They're going to have the same appearance. These are also called solutions, as you see in the picture on the top right. A later chapter will detail solutions and heterogeneous mixtures in much more detail. For heterogeneous, if we turn or look at that mixture from a different vantage point, we're going to get different appearances. Granite, those little rocks in the driveway, other kinds of rocks, even one rock that we can just pick up and look at in our hands, turn that rock to different vantage points, we're going to see much different. We might see shiny in one part, not so shiny in another part. Texture would be different, rough in one area, maybe smooth on another area. Look at rocks, you're going to see different appearances from different vantage points. Homogeneous and heterogeneous. Ready? That is all for the first set of notes for Chapter 2. The next one, we'll talk about the phases of matter and how a substance can change from one to another. There are 6 total phases of matter, or phase changes, that we're going to talk about with the 3 phases of matter: solids, liquids, and gases. Thank you for your attention. Good day.